So we're going to use this section to kind of review and pull things into perspective and also move forward a little bit, kind of laying the groundwork for section 6.4. Now I'm going to start by talking about a study I was reading about yesterday done by the University of Michigan. And they did a study amongst people 50 years old and older last year, May of 19, and they found that only 4% of these adults had used a telehealth, meaning you consulted with a doctor over the internet, on your phone, or on a tablet or a computer, etc. And they repeated their study this year. So last year, only 4% of this age group had done a telehealth consultation. What do you think happened this year with that percentage?
Greatly increased.
Yeah, it did. Now, it's certainly not that big, but it went from 4% to 26%. And, you know, there's a lot of concerns that they expressed here with this, but, you know, overall, to me, the encouraging thing was that a lot of people are reaching out and bridging this gap through technology. So that's kind of cool. But the question to you is, do you think they surveyed every senior to get that data?
No.
Probably not. It'd probably be either impossible or at the very least impractical to talk to every senior about that stuff. So what happens? So you get this population of people that are age 50 to 80. That was requirements. That's your population. But from there, we chose a sample because we can't sample everybody. If you could sample everybody, then the data that you collect there and summarize would give you a parameter. And if you're doing that, you're doing a census. Census. That's how you get from here to here. But doing a census, like I said, is impossible or impractical in most situations. So you collect a sample. And with your sample, you're going to calculate things like mean, standard deviation, or proportion, etc. But that's going to give you a statistic. And we hope that our statistic is a good estimate of the population parameter. That's what we're hoping for, because we can't get this very often. That's the gold standard. We'd love to be able to know the population parameter, but it's seldom the case that you can get the population parameter. Usually you have to do with the statistic, and that you hope that your statistic is a good estimate of the population parameter. So let's see and discover some things about using a statistic to estimate a population parameter. And I'm going to do it with an artificially small data set so that we can kind of grasp what's going on here. So that data set is this one right here. Let's see. Try that again. This one right here. So that's our data set. So it's these 5 numbers. The heights of an exceptionally tall basketball team, or at least a couple of them are really, really tall. Now, let's suppose that that's our population. And I'm feeling really lazy. I want to calculate the average height of this team, but you know what? I don't feel like conducting a census. I don't want to talk to everybody. So I'm just going to take a sample. So what if I took a sample of size 2? Well, how many samples of size 2 are there? Well, you can do this on your calculator. This is a good refresher there. You've got 5 people, you're going to choose 2. Can anyone get that from their calculator? 5, choose 2. What would you get? All right, so I'll tell you what, a little help here, a reminder.
I got
Of course
10.
Yeah, you should be able to get 10. So 5, math, over to probability, third one down, choose 2. So the other way you could get that number is simply by counting the number of examples I have here. These are all the different choices you would have. You have 10 samples of size 2. And from these samples, we're going to calculate the sample mean. So not really that hard, just add them up and divide by 2. So if this is your sample, that's a sample mean. Sample, sample mean, etc. Let's see what happens. Well, when you add them all up, average them, and then graph them, what you started out with was your population on this bottom line, samples of size 1. These are all the different members of your team. For samples of size 2, this is what you get. These are your different possible estimates. Now, I should note for us that in our population, if you were actually able to sample everybody, and of course it's not that hard in this particular case, but if you sampled everybody, the population mean is 80. So we're going to have mu equal 80. And so how do we do with our samples of size 2? Do our samples of size 2 provide a good estimate of the population mean? Okay, I mean, you can get some that are close and some that aren't so close. So, okay. I mean, not bad. But there is a nice feature that I want to point out. What if you take and added all these up? You'd get 800 exactly. Now, we know that there's 10 of them. So, on average, what's the average value of the sample mean here?
80.
80, yeah. So what that's saying is that, yeah, sometimes you're low, sometimes you're high, sometimes you're right on, but on average, this is giving you the right answer. The mean is 80, and your average of these samples is also 80. And what that does is that makes this what's called an unbiased estimator. So that's right here. Unbiased estimators include the mean. Because if you use the sample mean to estimate the population mean, if you use the sample mean to estimate the population mean, on average, you're going to get the right example or right answer. Now, any particular one could be low, could be high, could be spot on, we don't know, but on average, you're going to get the right answer. So that's good to know. What if I decided, you know, I don't have to be quite so lazy as to use samples of size 2? What if I use samples of size 3? Well, we've got a lot of different samples of size 3. And the interesting symmetry here is choosing the 3 that you want is kind of like choosing the 2 that you don't want. So there's 10 here. And a similar thing is going to happen. If you add all these numbers up, once again, you're going to get 800, meaning the average of these sample means is 80. So if you're using this as your guess, on average, you'll be right. Now, does that mean you're right in any particular guess? No. But, you know, you will be right on average. So let's take a look at what happens with samples of size 3. That gives you this data right here on the third line from the bottom of this chart. So n equals 3. Are we doing better with samples of size 3 than we did with samples of size 2?
Yes, because the data's closer together on the line.
Perfect. That's exactly what I wanted to hear. The data is closer together around this line. So that means you're not as likely to be far away from what you're trying to estimate. Remember, these estimates come about because we don't know the population mean, but we're trying to estimate it. So by taking a larger sample size, we're going to be closer to that population mean. Okay. Now, as ridiculous as it seems, our fearless statistician is going to sample 4 of these. Maybe there's somebody he doesn't want to talk to. Somebody unfriended him on Facebook. So he's going to only talk to 4 people out of the 5. So choosing 4 out of 5 is really like choosing the person that you leave off. And there's 5 ways to do that. Now, if you total up these, you get 400. So what's that saying on average? What's the average here?
40?
But there's only 5 people here now.
80.
80.
There you go, 80. So once again, you're getting 80. So the mean is an unbiased estimator. The sample mean is an unbiased estimator of the population mean. And now look what happens when we plot those 5 values. Can you really be off by that much if you're using a sample of size 4? I mean, the worst you can do is you'd be around here at 78.5 or 81, but you can't be that far away, can you? So, wow, what's happening? As you take larger and larger sample sizes, what's happening with your data?
Did it get closer together?
Yes, they're getting closer together. What statistic is it that talks about how close something is to the mean?
Standard deviation.
Well done. So the standard deviation is decreasing as your sample size increases, and that's cool. Basically what it's saying is that you're necessarily going to get a better and better estimate by taking larger and larger sample sizes. So, okay, yeah, that makes sense. Let's draw a couple important general conclusions about this. One of the most important ones, and this has appeared on tests from time to time, is this. X bar, your sample mean, is a random variable. That's the most important conclusion to get here. The value of this depends on chance. It just depends on who you pick to be in your survey, which typically is done at random. So X bar is a random variable. And as a random variable, we can discuss a couple things. What's the mean of this random variable? The mean of the random variable X bar is the same as the mean of the, where should I put here?
Sample?
Well, this is already from the sample. The sample estimates the population mean. Yeah, there you go, good. So the mean of the random variable is the same as the mean of the population. Sometimes you'll hear me call it parent population, and that's not parent with a capital P, it's parent with a lowercase p, because it's not me, it's just the population where that sample came from. So your sample mean on average is going to have the same mean as its parent population. And last but not least, as the sample size increases, the blank of the random variable decreases. What can I put in here?
Standard deviation.
Standard deviation. Thank you so much. Well done. Yeah, standard deviation. Nice. And you can see that visually, right? I mean, take a look here. Here's your original distribution. Samples of size 2, 3, and 4. And the spread is steadily marching down. So you take a bigger sample, smaller standard deviation is going to accompany that standard deviation there, or standard deviation of X bar. Nice. Now, I said that the mean is an unbiased estimator. Right now, maybe we don't have a real good understanding of that. So let me go back and look at something else from our data, and that would be the sample range. You remember how you find the range of our data? What was the range of a data set?
The highest value minus the lowest value?
Yeah, the highest minus the lowest one. So, okay, highest minus the lowest. So the range here is going to be what? 10, right? 86 minus 76. So the range is 10. Let's take a look at our sample range for samples of size 2. So it's going to be top minus bottom. Well, that's kind of easy math. And when I do that and sum all these up, I get 46. And because there's 10 values, I get 4.6 as the average sample range. Now, how does that compare to the actual range? The actual range was what?
10.
10. This doesn't seem to match it. Now, it did with the mean. The mean of my original data set was 80, and the mean of the samples I chose was 80. So that was an unbiased estimator, but that's not the case with the sample range. The range is a biased estimator. So you can see that on our sheet here. The range is a biased estimator, meaning on average, it doesn't give you, what you're looking for on average. I mean, there was one value where it did, but more often than not, it didn't. So it's biased. So I'm hoping you're getting a little bit of a feel for biased and unbiased estimators. On average, you get the same answer as your population. Here you don't. Cool. Cool. Now, I've thrown a lot at you, a little bit more challenging than usual. How are we doing with this stuff? Some of it making sense? Is it getting through? So what are the highlights here that you should know? Well, the highlights are down here. First of all, X bar is a random variable. This quite often is like a 2-point test question. Fill in the blank. X bar is, a random variable, because its value is going to depend on chance. And as a random variable, there's going to be 2 parts to this. It's going to have a mean and a standard deviation. The mean is the same as the mean from the population from which it was sampled, from which the sample was taken. This was taken from a population with a mean of 80, and guess what? Its mean is also 80. As you increase the sample size, the standard deviation of your random variable, the standard deviation of X bar decreases. That is, the spread is going to narrow. And that's good, because it means as you take larger and larger sample sizes, you're closing in on the value of that parameter. It has to be closer and closer to your data as you take more and more samples. You should also know the difference between population and sample, parameter, and statistic. A statistic is something that estimates the population parameter. Why are we doing an estimate? Well, because it's impossible or impractical to do a census. So you have to take a sample. And then here's some notation here for you. Down here in the middle, and that is X bar is the sample mean. And it estimates the population mean, mu. How about S squared? Does anyone know what that is?
Is that the variance?
Well done. That's the variance. And that estimates the population variance. All right, cool. Now, if we had the population variance here, or excuse me, if the sample variance here, what's the square root of that going to be?
Standard deviation.
Good. Sample standard deviation. And last one, P hat. And I don't know why, maybe it's going back to the days where I watched Dr. Seuss, the cat in the hat, chapeau. I think of this as P chapeau, but a lot of times it's called P hat. And in any case, P hat is a sample proportion. Sample proportion. So the sample proportion estimates the population proportion. And it's just regrettable and nearly unavoidable that we're using P an awful lot. We use it for probability, we use it for p-values, we use it for proportion in the sample and proportion in the population. P gets overworked. Sorry. There's enough Greek letters around that I don't know why they don't do something different, but that's the world we live in. Cool. Now I would know based on just memorization, rote memorization, what are the unbiased estimators? What are the biased estimators? So this is your list. Keep that in mind. Keep that as part of your notes. Now there's one problem that I think that you'll see in the homework that kind of goes over the same thing here that we did with the means. It's doing it with probabilities, and actually not probabilities, but proportions. So it's trying to show you that the sample proportion is also an unbiased estimator. And they do that by asking you to complete this table. You've got, let's see here. Can I write on this? First of all, are you seeing this? This is talking about, you know, two babies being born, and the sample space is either boy, 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 girl, girl, boy, or girl, girl. And they want you to estimate the proportion of girls that you get from this experiment. So there's a 1 in 4 chance you'll get 2 girls, 1 in 4 chance you get 2 boys, and a 50-50 chance you get 1 of each. So to show that this is an unbiased estimator, what I could do is just calculate the expected value here. So let me write down our probability distribution, x and p of x, 0, 1, and 2, 1/4, 1/2, and 1/4 again. So if I calculate x times p of x, it's going to be 0, 1/2, 1/2, and let's see, 1/2 again. So the expected number of girls is 1/2 plus 1/2, which is 1. And that will give me a proportion of 1/2. So of the 2 girls, or of the 2 babies, we expect 1 girl, a proportion of 1/2, 1 out of the 2. And I'm sorry, I should be zoomed out a little bit. So So there's your answer to one of the homework problems. This is an unbiased estimator because the proportion that we get matches the population proportion. So it's kind of a contrived example, I admit that, but it's just, it's hard to show the unbiasedness of these estimators with much bigger examples. Okay, how are we looking on section 6.3 there? Doing all right?
Yeah.
Okay,
Worth.
all right. We'll call it a day here.